series, right? So today we're very happy to have with us Professor Peter Fritzon from Linköping University, where he's a professor and research director of the Programming Environment Laboratory. Professor Fritzon has a very long and excellent experience in all kinds of issues that have to relate with model-based design of systems and controls. He's the director of the open source Modelica consortium, to which I'm happy to announce we are now members of SISR, and director of the ModProd Center for Model-Based Product Development. He's also vice chairman of the Modelica Association, an organization he helped establish, both of them. So in the period of 1999 to 2007, he served as chairman of the Scandinavian Simulation Society and secretary of the European Simulation Organization, Eurosim. He has a lot of interest around software technology, especially programming languages, parallel code computing. He was one of the main contributors and founders of the Modelica language, which we have heard, at least in this institute, from the very beginning. We were collaborating with Sweden at least since '85, right? Even before that. And he has co-authored more than 200 technical publications, including 16 books and proceedings. As I said, he was a great assistance to us to become a member of this Modelica organization, and we now we have access to all that. And today he's going to talk to us exactly about Modelica, a cyber physical modeling language for systems engineering and the open Modelica environment.
Thank you.
Welcome.
Thank you, Jan, for the invitation to come here. This is my first visit to University of Maryland, and as I can see, it's a quite nice campus and impressive university. And I hope I will be able to return here, and that our cooperation will get a lot done in the coming years. So let's start. So I will talk about Modelica and the various aspects of the cyber-physical modeling. So why not start with Modelica, and then you can start back in history. So this project with the Modelica language started in '96. Modeling language we had before, and there is a lot of knowledge in books, engineering knowledge, scientific knowledge. You have capturing some knowledge in equation. For example, Newton's equation here, second law, written in Latin, because Newton wrote everything in Latin. That's a bit interesting. So even though the equation sign was invented 100 years earlier, that was in Swansea. I know that because I was giving a talk a few years ago in Swansea, and I walked by the Robert Record conference room. So it turned out that he was from that place. It's only 200 kilometers from Oxford, but the equation sign didn't propagate to Oxford in 100 years. Then information propagation was a bit slower at that time. But anyway, most programming languages, they use the equality sign, but they fool you because it's not equality as in high school mathematics or mathematics. The equation sign has been converted into an assignment operator, which is quite different. But in Modelica, equality means actually equation. So that's one of the languages. Here, what is Modelica then? It's a language for modeling complex cyber physical systems. And for example, here you see the Modelica simulation of the Swedish JAS Gripen military aircraft. That was a library developed by our spin-off company. You can also simulate, which we are not doing here, the fatal ruling which ended with a crash of some of the other prototypes. But there is quite a range of applications from robotics control, automatic aircraft, but also systems biology. I have to teach these students for a while in that area. One of them made a library called BioCamp for pathway modeling. That's actually available as open source. We continue a bit. So Modelica is a language for modeling complex cyber-physical systems. So primarily for simulation, but increasingly used for other things like optimization together with models and generating embedded code. So Modelica is a language, not a tool. And the language is defined by this document, the Open Language Specification. It's standardized by the Modelica Association, which is a standardization organization. But not only that, it's also promoting its development. And there are at least 7 tools around. Here are some of them. So I will talk mostly about Modelica from the open source Modelica consortium. Here is a tool called Math Modelica from MathCore, which nowadays is owned by Wolfram Research in the US. There's Daimler Industrial Systems, which is the most widespread industrial tool. There is another industrial tool from a German company, Maple Steam, you know about. It's from Microsoft in Canada. So Modelica has a number of nice properties. It's declarative, which means that you can state equations and functions. It's multi-domain, so it's not for a single application domain. You can use it for many different applications. Areas, write libraries for different areas. And everything is a class. It has a uniform design for feature component programming. It's designed to be efficient from the start. Strongly typed language. So causal modeling is a key factor in Modelica because I started talking about equations. Causal means that you have no causality in a certain direction. If you have an equation, 2 things are equal, so there is no direction there. But that means that you can actually, when you solve it, you can compute in a certain direction, but you have a freedom. The models. So an equation here can be used in 3 different ways depending on what you compute. This means that causal models have better reuse than traditional algorithmic, which you can see also in software where people try to do reuse of component models. They typically use assignment statements with fixed causality, and then the models have less flexibility. I will focus on 4 properties of Modelica: multi-domain, visual, type, declarative language, and hybrid modeling and simulation. So let's start with multi-domain. Here we see mechanics, electrics, and control mixed in one model. So we use model components from 3 different areas. Hierarchical component modeling. Here is an causal model in Modelica where we just connected a few components. Here is a causal log-based model, which is typical Simulink signal flow model, even though nowadays there are also libraries supporting causal modeling in Simulink, like C-mechanics. So this keeps the physical structure, whereas the other one you have to convert by hand to signal flow. Hierarchical system modeling is quite important in order to handle large systems. Here is an ABB robot. Here is the top level of another robot. You just see a few things, motors, gears on the top. Then you can expand. So you can see more detail by looking inside. You can expand that. Then at the lowest level you have equations. So here we have some Newton equations with 3x3 coordinate transformation matrices. Typical when you have robotic arms and so on. This has been made at DLR, Martin Otto, where they work a lot with robots, industry robots. Then we have the language. So this Modelica language is, as I said, it's standardized. There's a standard document, and it's textual language, even though it can be used for graphical modeling. But it's nice that it has a textual representation in addition to graphical, because sometimes textual is better and you can do more concise programming. But if you do the graphical, you can use the Modelica standard libraries. The object orientation is used as a structuring concept. So it's used for decomposition of complex systems. It's used for inheritance, for specialization. But it's not used for message passing, as you have in Smalltalk. But if you start in the history of object-oriented programming, starting with Simula, there was actually no message passing from the beginning. We had classes, we had behavior, objects, and methods. In Modelica we don't have methods, but instead we have equations for expressing behavior, and also functions. There might be perhaps a limited form of method in the future, but we are trying to keep the mathematical properties of a declarative language, which means that the functions, when you call a function with certain inputs, they always give the same results. It's like mathematical functions. So that makes it easier to use it for high-level specifications and keep correctness. So correctness checking is two ideas that, and efficiency are three ideas that we try to maintain with Modelica design. So for example, in MATLAB, which is an interpreted language, it's not checked before you run it. You have to test a lot of test cases and hope that you catch the bug. And because Modelica is strongly typed, compilers try to catch as many bugs as possible before execution, because it should be a language for safe engineering. That's one of the main design goals. For example, in Modelica 3.0, it was introduced balanced model checking, so you can check model components also for balancing properties. Here is a small piece of Modelica with two equations, derivative of x equals y and so on. And these are start conditions for the solution that you can attach to variables if you wish. And hybrid modeling is the fourth important property. Hybrid means that you can combine continuous time and discrete time. Of course, discrete time is an approximation in physics. Essentially everything is continuous, even if you have quantum switches, but then you have probability functions for the transitions. But the discrete is a very useful approximation that can simplify models, for example, a switch between 0 and 1, instead of describing the physics, the detailed physics. So hybrid, you can mix and continuous time and discrete time in the same language. And the solver and the compiler is taking care of that. The graphical modeling you can do in a graphical tool like this. This is the graphical editor in the Open Modelica open source implementation. This tool is rather new. We released the first version a year ago. And we are not very far from the commercial graphical user interfaces in this one. Before that, we had another graphical user interface which was not as good as this one. This is pretty fast and reliable, and has many of the commercial features. A small example of a multi-domain Modelica model. Here is the diagram that you can draw using the graphic. So it has a mechanical load, electric converter, and a new electrical. You can see here that the
text that's generated here contains a declaration for each component, and that each line here is trying to put a connect clause. This connect clause doesn't look like an equation, but represents at least two equations. It's just that it's easy to write syntax. So these connects here expand into two equations here, according to Kirchhoff's laws. For example, the resistor becomes four equations because there are some inequalities connecting the port variables. Then the whole thing will become an equation system that's used for simulation. So generating this form is called flattening, because we remove all the object-oriented structure, inheritance, and so on. And here you can see the process of flattening. Starting from the graphic or textual modeling, the source code here is a translator that's transforming it to a flat, hybrid, differential algebraic equation system. Then sorting equations according to dependency analysis, optimizing. Typically only between 10 and 20% of the equations are actually needed in the core equation system. Numerical solution, all the rest can be separated, which speeds up execution quite a bit. And it's co-generate, and typically we generate C code, C compiler, and simulation. But we also have alternative code generators in Open Modelica. We have a C# code generator because one guy in the Czech Republic likes to use C#. He's using the Microsoft platform. And then we had a master student do a Java code generator. And then we have another C code generator for parallel C, for the OpenCL. Yeah. Some applications. Here is a gas turbine application developed for Siemens. Is replaced. They have worked with Simulink 2-3 years to get the model. But they never got working, so then they switched to more physical modeling style. This works rather well. It's within 1% of the measurements. This is the avionics model that I showed in the aircraft before. It's just a small part of it. Automotive industry is one of the main application areas of Modelica because you have a lot of different physics there. You have a combination of mechanics, electrical systems, cooling systems, as well as electronics. So, for example, in Germany, all the big German manufacturers use Modelica, especially for the tricky products. Also in biomechanics and biology, we have some applications, even though it's not so much yet, but it's just because of tradition. Here is a real-time robotics application from the Deutsche Luftraum in Germany, Martin Luther. So this is a training simulator. Here, two people are sitting up here, and this big arm is moving around, so they feel acceleration. All the models behind this is in Modelica. The control is written in Modelica. So they can look at the screen here and experience that it might be like flying.
flight simulator.
Okay.
This as important as a language is the standard library, also developed by Modelica, which means that in reality lots of people, experts in different areas, develop their own libraries and then contribute it as open source. There are people in different areas that have contributed these different libraries. There's also been big European projects that developed about 30 libraries. About 20 of them are open source. So the Modelica effort started in the fall of '96 with some meetings regarding publishing a white paper about object-oriented modeling language. But it actually developed into a design effort, which nobody of the participants would have imagined that this would happen. Still going on 15 years later and has expanded quite a bit. After 1 year, we released version 1. I remember that because we had a small document we put on the web and the photo and so on. And we felt we had achieved quite a bit, but it turned out that this was just a small beginning and there were a lot of things missing. In this document, some of it we found when our group started to do a formal specification. That formal specification later developed into the Open Modelica system. But then the effort has increased, more people have added, and here we are now. 3.3 should be fall 2011. I did a small typo here. And we started a conference series 2000, and the last one was in Dresden, Germany. Also there is a series of Open Modelica workshop. The fourth one will be February next year in Asia. So let's talk about the tools a bit. So this Mass Modelica is a commercial tool. It's nowadays from Wolfram Research. It was developed in Linköping, but it's now being integrated with Mathematica. So it's both working in the US and Sweden. Here's a car model where you can see you can design your own icons. And I should mention that this tool also has special support for biological simulation with pathways, and has export and import to the system biology markup language. Here's a car model simulation animation. MapleSim is from MapleSoft. So for a while they were partners of MathWorks, but then decided to go on their own. They selected Modelica for their modeling and simulation tool. And it's fairly recently that they released the first version of MapleSim. Daimola is from Dassault Systems, one of the major CAD vendors. It was first a small company in Sweden that was sold to Dassault Systems. This is expanded and integrated in the tools, design tools of Dassault. Simulation X is another Modelica tool. They started with their own language, then converted to the Modelica language, and also converted their libraries to Modelica. Then we'll talk about the Open Modelica environments, which is my pet project since I'm a director of the effort. So it's the most complete open source Modelica tool. It has several subsystems. You can see some of them here. Here's the graphic editor, here is the optimization subsystem, here is the electronic book. it's a textual interface. But the most important part of it is the model compiler, which shown here is an interactive compiler. You can run it in two modes, either in a batch mode or as a server in a command mode, where you send commands and get results back or evaluate expressions. And there is also a UML profile. You can see it here briefly. That Modelica ML is actually like second generation SysML. We talked a bit about it earlier today. It also supports requirement formalization, requirement checking, and some other things as code generation, so you can actually simulate and check for models. It can translate UML state charts and activity diagrams, for example. Then there is also an Eclipse plugin called MDT. We use that mainly for the compiler development. It can also be used for Modelica library development. So those are, you see there are a lot of subsystems. We are now, the path is to integrate. This is one Eclipse plugin and that's another Eclipse plugin. Both are implemented in Java. In the long run, we would like to integrate those two. One is very good for textual modeling, the other one is good for UML, SysML style graphical modeling. And to run this, we have the open source Modelica consortium with 34 organizations right now, and I'm quite happy that University of Maryland now is a member. This was started with 7 members, 2007. We have a lot of distributed development. We have Skype meetings every Monday. So developers in different countries check in their contributions. And the Skype meetings is an informal way of discussing things. So here you have the members right now. Companies, some big companies, Siemens, ABB, Bosch. Some smaller companies, also some institutes, universities, and countries in Europe, India is there, US, and so on. We'll mention a few of the subsystems. So this electronic book here, the reason we created that was it was inspired by the Mathematica tool. They also have an electronic book. And we used the Mathematica book for several years. But we had the problem that many people didn't have Mathematica. So that was a problem to use it for teaching. So we implemented a lightweight version of electronic notebook as open source. And then we used it to, for example, create a control course here, doing teaching control together with Modelica. So you can have the plant model in Modelica, but you can also use some of the different controllers, PI, PID, etc. you can find in the standard library.
How many courses do you have on that?
Right now we have 2 course materials. One is called Dr. Modelica, that's for teaching object-oriented modeling and simulation. That's using the models in my book that are available for download. Then Dr. Control, which is intended for a control course. And that's rather recent, so that's not.
You don't have a Docker system engineering?
Pardon?
Docker system engineering?
No, but yeah, perhaps you can do one. So, small demo. So here is the graphical interface. here. Just take some components. And do the simplest possible circuit. And then there are several sub-libraries. Here we have sensors, semiconductors, etc. And the sources, signal sources. Take a simple signal sine voltage here. And then we turn that around because so we have the plus up here. So take this. So let's hope that this is connected. Simulate. Now it's compiling it to C code. And showing some diagrams here. You can expand here if you like to see some more curves. Here you can control the curves you see. So that's basically it. Then we have interactive simulation also. So you can control the running simulation. This is the Eclipse plugin. You can see, get information on functions on, as you have, for example, the C or Java Eclipse plugins, with outline and so on. And there is a new debugger becoming operational now. That's quite efficient. And essentially no overhead if you have a 100,000 line model. But that's restricted to algorithmic code. Modelica right now. Then we have a prototype on an equation transformation debugger to explain if you have performance problems or it's computing the wrong result and it's executing the C code that's been generated. What is influencing that? What parts of the models? And that's not easy to realize by yourselves. It's important to have an explanation. That debugger can work on. It's a prototype that's not in the release yet. Optim is parameter optimization subsystems, so it's can do many runs and select the parameters that give the optimal results for the call function. And it can also have Pareto fronts, so it can optimize two different combination of different call functions.
What freedom you have to put the algorithms in this?
Choosing, yeah, it's open source, you can do whatever you wish, but right now it's genetic algorithms
if I want to change from genetic to something else, can I do it?
Or if you,
If I want to change the optimization algorithm to something else, can I change it?
yeah, you can do it by hand by changing the source code, but in the future you would like to
Be able to link.
be able to link in a more efficient, easier way. This is a graphical user interface. You can run it with Open Modelica, but you can also run it together with Modelica, for example.
Is it possible to connect this to MATLAB and use the MATLAB optimizer for doing
Yeah, if you, since this is open source, you can do it, but it's not done in the current tool. You would need to do it with the programming interface code.
If Georgia Tech has done something like that, and also some people are talking about, so the person who has done it in Georgia Tech is coming to talk here about 3 or 4 weeks later.
Yeah.
Professor Paris, and they have worked together on some of the model cases about.
So there is room for improvements and contributions from the students and others. Concerning calling other languages, there is external function support for calling C and Fortran. That's in the Modelica language standard. And we also implemented Java calling support in Open Modelica. That's also available in Java, but that's not standardized yet. Then there is an interesting development called Functional Mockup Interface, FMI. This is standard for model interchange and tool interoperability. It's an open standard, you can find it on the web. It's run by a big European project. It's 29 partner project, saying that it's about 250 man-years in this project. It's quite a big effort. And the main goal of the project is this interoperability standard. And that was actually Daimler that changed the project, so that would be the main thing.
So it's open now.
Pardon?
Now it's open stuff.
It's an open standard, it's been published. And there are open source
So they have AutoSAR controller models in this? All of them? Or?
There are, it's also about integrating Modelica with AutoSAR. And most of those things are proprietary from the source system, for example. But,
Which things are proprietary to that?
pardon?
Which things are proprietary to that?
I mean, some of the,
AutoSAR.
I mean, the tools in the source systems for coupling Modelica with AutoSAR. But the FMI standard is it's an open standard, even though most of the implementations are proprietary, except for there are 2 open implementations. Open Modelica is one, and J Modelica is the other one.
For FMI?
For FMI, yeah.
Ah. Because this tool interoperability is becoming a big issue.
Yeah,
with
and
companies, with companies,
it's a
right?
big issue because Daimler, as an automotive company, they have several hundreds of modeling simulation tools with incompatible formats, and they want to simulate the whole car.
Right.
They actually do quite a bit of that. So they have finite element tools like SimPack. They have several different simulation tools, special purpose, mechanical. They have Simulink. They have Modelica. And because they have this problem, they want to run everything together. And now this is on the way, actually. So it's more than 10 tool vendors supporting the standard, and it's increasing.
In these use cases you have, say you have automotive, 14 automotive use cases for evaluation.
Yeah.
Do they have anything like what what I might want to call impact tool.
What do you mean impact?
I go and change the battery or some requirements about braking or something about one of the components of the car. Can I see what other things are affected?
Yeah, that's different kind of tool. But of course you could use the FMI to simplify the realization of such a thing, because then the vendors making the components could actually deliver. You could have different component vendors delivering their models in precompiled form. So you can link in, and so what happens here, for example, is if you export a model from Modelica, it's converted to C code or that can be compiled into DLL, and it's associated with some information about the ports and variables as XML. This means that the importing tool can then recognize the variables, it can run the simulation, but if it's compiled code, it can't look inside, it can just execute. So, and there is a co-simulation standard that's on the way, that you might put us here. So I should speed up a little bit. We also have a project called OpenProd. It's a 28 partner project. I'm the scientific director. And here we have the goal of having an integrated modeling and design environment, starting all the way from business requirements to design requirements, then modeling phase, compilation and code generation, to system simulation and software products or system products. And in the project we have now working prototypes in all these phases, even in the process very early phase. So one piece of work in that is this Modelica UML profile. The idea is to combine software modeling in UML with hardware modeling in Modelica, because then you can model the whole system that's composed of both software and hardware. And UML is used for software modeling by many companies, but they mostly use it as a structured documentation tool. There are a few companies that use it for executable models, subsets of UML. And this is, I would say, second generation SysML. Then we are also part of a working group in OMG, myself and several other people, most of them in the US. So we have done a standards proposal for mapping part of SysML to Modelica in a well-defined way. But then we are doing research, and we would like to do things that are not available now in SysML. So therefore we have the Modelica ML profile. But you can use standard UML, for example, activity diagrams here, or state machines, and then you can do your design in that way. And then you can add requirements. You can have textual requirements like this. Then you can formalize many of these requirements and express them as equations. Since they are expressed as equations, you can associate them with your design model over here. Then simulate and check whether the requirements go. So here two requirements are, there's a violation here because a certain requirement for a tank is violated, that it should be below a certain level here. So there is, in this profile, there is code generation from activity diagrams and state charts. So Modelica, which then can be executed by several different Modelica tools.
What's the best connection you have with the finite element models and 3D, 3D plus time?
Yeah, there are two different connections. One is the SIMPAC finite element tool. They have
SIMPAC?
SIMPAC has a FMI connection, and And then we have our the Modelica PD prototype from 6 years ago. There we did two versions. One was to represent differential equations using method of lines as differential algebraic equations. The second we did was to connect an external finite element to.
If I want to do a photovoltaic array,
Pardon?
I want to do a photovoltaic array,
What?
a photovoltaic array, I'm modeling, and I want to model the chemistry, and I want to model the properties and so on and so forth.
Yeah.
What can I do now with Modelica?
What? It depends what you wish to do.
I want to do the material properties, I want to understand the absorption, the thermal. So if I go to console, okay, I can build a fairly sophisticated model of that.
Yeah.
But I cannot do some of the other things. I cannot do block diagrams, I cannot do behavior, I cannot do
Yeah, that's the
power.
problem. You would like to have both.
Yeah, I would like to have console linked to Modelica.
Yeah, yeah. So, and that's not possible right now.
Is anybody working on that?
I don't know. But if you use SIMPAC instead of console, then you can connect it through FMI. That's the only answer today.
CPAC is open?
No, it's a commercial tool. It's just like console.
Okay.
And we have plans to restart the work on PD extensions. And if some people here are interested, we could
I would definitely.
collaborate. Because my group, we are quite interested in compiling Modelica efficient multi-core code. And then PD models are quite interesting because you get many equations. It's good for realization. Anyway, speeding up, there is online interactive simulation also. There is a meta Modelica language extension for model transformation, because during compilation we transform the model in many stages down to a form which is close to C code. But you could also do things like symbolic differentiation of equations. That's done, for example, when computing symbolic Jacobians. That's implemented using meta Modelica. Other transformations you would like to do. I would like to point out that this is a very efficient transformation language. It can process a very large number of nodes in a very short time. And it's a compiled transformation language compiled to C. So we have the largest application is the compiler itself. So a few words about parallelization, compiling parallel code. So we explore parallelism in model equation systems, also coarse grain and explicit parallel programming. Here is one example of it's an old example of extracting some parallelism on from Modelica model by grouping operations like that, and for example executing that on one processor and that on another processor. We need to group small tasks so we don't get too much communication overhead. Here we get speed up at 2.5 on 8 processors. Our problem so far has been also that we have had two small applications and the prototype didn't take the big applications, but we are getting to the big applications now on the second generation. Here you can see parallel equation tasks in the 2006 prototype, but the solver is still a sequential bottleneck running on one processor. In the later version, we spread out the solver on 3 different, so we took during Kutta, that was pipeline. So parts of the solver could run on 3 different processors. So then we got a factor of 2 or 3 faster code. Here is some work on NVIDIA GPUs. Cards, they have an enormous number of processors, but they are mostly good for data parallel to computing, so compute the same operation on each processor. But they can do a limited amount of functional programming, task parallelism. So you see standard Intel is faster, but for large problems the GPU is faster in shorter time. Here is a bit of the GPD problem. We extended the language here with domains here and handing down their conditions. You can download the PhD thesis if you're interested in that. And then I think I will speed up a little bit the little language concepts. There's only a few minutes left. So I would say we have Modelica functions, just like in other languages. And there's inheritance. Between classes you can inherit equations. There's multiple inheritance. You combine geometry, for example, and color. And there is something called modifier. You can combine inheritance with the declaration equation that gives a more concise code for a modeling language. And then we have the hybrid systems where we can combine, as you see here, continuous dynamics with bound discrete events, the bounces. So continuous variable and discrete time, and then you can associate event conditions here. Two kinds of variable, continuous and discrete. Then you can have so-called if equations. So if off is true, then this equation holds, otherwise that equation. So it can switch these equations at runtime very efficiently between different modes. So compiler takes care of that. And certain equations are already active at events, so-called when equations here. They are only executed at the events that they are passive to.
If I do that in a hybrid system, do you have checkers for that I won't get deadlock, for instance?
There's no deadlock checking built into the current tools, but there has been some prototypes.
What about correctness of semantics of time? Do you have to check for that?
I can say there is a lot of work now done in the design group on the second generation hybrid properties. So many of the things that you find in languages like Signal and Listre will soon appear in Modelica.
So you're going to put Lustra things in here, or
No, but the language properties.
language properties?
So the clock, synchronous clocks,
Right.
and be able to extract the clock handling and those pieces. And then you can do the same analysis as in those.
When is the synchronous part coming?
It will come in Modelica 3.3, so it's scheduled for December, but if there is a delay, it will come in early spring.
Okay.
So it's just within a few months. There is also prototyping going on in a few tools. There is also repeated events generation, discontinuous change when you have, for example, bouncing ball. When the height becomes less than 0, you can reverse the velocity. And then Modelica libraries, these ports here, they are also defined using classes. You have two variables here defining the interface. Essentially everything is class in Modelica. Real variables in the class, the ports are defined by classes, and the models are defined by classes. And despite that, you don't lose performance because it's a strongly typed language, compiled language.
So the connector itself can be a system?
The connector is a class that can't have equations.
You cannot.
No. It's only intended for as an interface class.
So if I want to have memory in the connector or some logic, how do I do that?
Then you create a class containing that, and then you attach it to the connector.
Oh, okay.
So if you have a pipe where you have some physics and you do pipe model, then you do put connectors at the end to have the attachment to the other one.
Is there any way to check if I do connections, if what I end up is meaningful or I have a problem?
Yeah, the types of the connectors are checked by the tools. If you connect incompatible connector types,
You want me to do?
it won't let you do it. You saw this graphic editor, it won't let you do it.
So that's why you're trying to keep it there.
Yeah, connect. But there can be errors even if you connect it the right way. Because you can forget connecting something that's needed. The ground is needed for something in electrical. So there are flow variables and potential variables in connectors, and there are, depending on the physics, we have different connector classes. So we have electrical, mechanical, rotational, translational, magnetic, chemical, hydraulic, etc. So designing the right connector interface needs some experience from the application area.
If I wanted to study stability, can I take some of these variables and let's say the potential variables and make it a Lagrange function?
And make
The Lagrange function?
what kind of function?
Lagrange function.
The
Can I do things like that? If I go and have some potential function, can I connect them and make a Lagrange function and prove the stability or anything like that?
I mean,
I'm trying to link the modeling to performance questions. That's all.
Yeah.
We are learning things.
We've done a performance analyzer, but that's based on measuring the runtime performance on different parts of the model.
Because we have some sort of theory that people have done a program of dissipative interconnections and all that stuff, that we can actually show that how to interconnect systems so you can maintain stability as you interconnect.
We're thinking about the system stability controlling in a way.
Yeah.
Okay, that's
So
probably.
we want to be able to project stability margins and things like that from the components to the overall system and back as we go along.
Yeah, that's probably outside my area since I'm not a control specialist, but a computer science person.
Thank you.
Yeah. Anyway, Kirchhoff's laws are used for expanding a connect into equations. And then you can reuse common component structure here. Even for many components have 2 pins. You can inherit that. So here you can then extend, you inherit the 2 pin and you just add one equation and you get a resistor, or you add inductance equation, you get an inductor. So in this way you can reuse a lot. And this is how you create a library. You create some incomplete model, like shells, and then you add some equations. You can create components in that way. This is a starting point of a small electrical library. So the Modelica standard library for graphical modeling is open source. Here you have many of them, but this is a block diagram, continuous discrete, logical, electrical, mechanical, 1D and 3D, state graph, which is a bit similar to state chart. And here are some other free libraries, bi-state, for example, electronics, vehicle dynamics, quantity, etc. And some commercial libraries. And here is my thick book, came out some years ago, International Use Case. You get a lot of pages for your money. It's only 2,000 pages, it's a good price per page. The reason it's thick is contains both a description of the language and quite a lot of examples, some explanations behind, for example, the multi-body library. I try to dig into it a bit. There is also a overview of some of the numeric and symbolic techniques. So it can be used as a reference, or you can extract selected parts for a course. Then I came out with a book this month which is much, much smaller. It's intended for introductory courses or where you would like to learn a little bit of Modelica as a part of another course. So if the other thick would be scary, this is quite thin and shouldn't be as scary.
Are you planning on having a new edition of the thick book?
Yes, I'm planning on that. I'm actually working on it. So I'm trying to get some time now and then. And I've updated many of the chapters, but there's still a bit of work left. And it would fit well time-wise together with the coming 3.3 standard, which would be good because then we'll also get the improved synchronous features. Okay, to coming workshops, you are quite welcome to come here. Linköping, Sweden, there's an open Modelica workshop in Montreal, and John is an invited keynote speaker. There was a workshop here. So, thanks for listening, and if you are...
Thank you very much. Is there any questions? Professor Fritzson said we are now a member of that, so you are welcome to use it and participate and create models and put them in and see what people say and so on and so forth. We plan to do more of that with students and faculty with their help. And we're also going to start with their help a Modelica course that they offer in Sweden, and we're going to try and offer it here for students and faculty, which has a lot of online features. So you're more than welcome to get active. As we say in software, if you don't write, you don't learn. Questions? I include myself too.
Okay, so when you start out, you're describing Modelica, you make a big deal about the fact that you've got classes that's very object-oriented.
Yeah.
And then you turn around and you generate code that's C. I mean, I understand why you did this, because back in the mid-90s, that's probably all you had. But if you generated code that was object-oriented,
Yeah.
I mean, what are the issues? I mean, do you lose something by generating C code versus, because then you can preserve the structure in some fashion, or am I just wrong?
There was actually early prototypes that preserved the structure more.
Yeah. And
Yeah, the code was slower.
oh,
There was several times. But there is one commercial tool that has separate compilation. That's the IDA simulation tool by a company in Stockholm. That's the only commercial tool supporting separate compilation of models. So they preserve some structure there. And there's discussion when one should do that. But it's been basically a performance issue that the simulation runs faster if you do more processing like this.
so is performance the only thing that matters?
No.
What else matters?
I mean, flexibility, separate compilation, and so on. So I think there will be some change in in the coming years, because there's a discussion that we need more flexibility, incremental compilation, be able to switch models at runtime with more flexibility than in the current Modelica. And there are some prototypes being done with structured dynamics where you can switch models which don't have the same number of equations.
Yes.
So there are some prototypes around. There are some papers in the EOL workshop series on that topic.
Other questions?
One could think about using just-in-time compilation also for more flexible.
So in the institute we're interested a lot in many aspects. There is already a small group working on microphysics models. So already we welcome chemical engineers, and other people into that. And we're not tied to just Modelica will be one of the modeling tools. We have others that we like to interpret. Particularly in this world, we are interested a lot in PDE models and things like that, because we're working are macro robotics. There again, for the material robotics, we do that. So, but in general, we want to go to multi-physics type. This seems to be a good way to do that. And we are also becoming a member of the Daimola organization. So we're going to be getting all the Daimola stuff as well, as academic partner in that. That has some pretty powerful stuff. So if you are interested, contact me or Shan or Mark Austin, and we will get a bigger group working. These things work interactively. We don't have to meet. We will be meeting, but you can actually participate by going to the page and so on and so forth. We try to make this available. It will be done through the Sim Lab, but then you will have accounts and you can use things. Okay. And we will have a collaboration with Lichoping in this area, which means you can visit there and they can visit here and so on and so forth for other places. So we intend to have a lot of activities that area. Basically, because of cyber physical systems, there are a lot of us work here, and these are other things that are becoming important.
People who like programming hacking tools, we have a developers meeting in the fall and another in the spring. The theory is you put a lot of developers in one room for a week, and then at the end of the week we have a lot of good results. And it actually works to some extent.
How compatible Open Modelica spatially editor is with Mac systems, or does it matter? Does it not matter? Because I remember back
With Mac systems?
Yeah, because I tried to see it. I went to your website a while ago and tried to get it to work on the computer. I had little issues, so I was wondering if
Yeah, the Mac version is not as, the graphical user interface is not as stable. It's quite good on Linux and Microsoft, but on Mac,
We recommend Linux for the open.
But we actually bought the Mac computer primarily to fix that.
okay. So it's on the problem.
So some work has been done during the past year, but there's been so much to do, so we didn't put the highest priority on Mac support, even though we put some efforts into it. So I expect it will be gradually improved. Of course, you can run the emulator on the Mac also.
Any other questions? So what we will contribute to that is our strength, which is optimization, trade-offs, things like that. So we are already working on that. Trying to take our tremendous tools in optimization, trade-off analysis, and so on, so try to link to this.
Yeah, and we have a Swedish national project for 3 years,
Good.
combining modeling and optimization with the optimization research group at each of the university, the vehicle systems.
Because as you heard me say here in last May in my talk to the technical sciences working, one of the problems with model-based system engineering is there isn't a very good link between trade-off tools. We have optimization, constraint-based reasoning, and this modeling techniques. And that will be recognized by the best people, and we are working on that. And another group that's working on that within the IBM tool set is IBM sets in Python. Try to bring CPEX and E-log in connection with Rhapsody and the other tools, right? So there won't be one tool. We talked about that. There will be a set of tools. So what we are hearing from industry and the software people is that the key is to be able to have interoperable tools. Both at the modeling level and at the implementation trade-off and at the requirement level. That's how the current version of model-based system engineering is evolving. It won't be one fit all. It will be different tools for many reasons. One of the principal reasons being that many companies get their own proprietary tools, and they will be able to connect to the core of common tools that they are not willing to disclose those. Okay. So get involved. It's very appropriate for our institute to do that. And you're more than welcome. Thanks for coming. Okay.